Welcome to chapter 12.1. This is where we are going to learn about forces. So a force is just a push or a pull that acts on an object. A force can cause a resting object to move, or it can accelerate a moving object by changing its speed or direction. So if I have an object at rest, in order to get it to start moving, I have to apply a force. If I have an object in motion, I can only change that motion if I apply a force to it. And if I apply a force, I can get it to speed up, slow down, or change direction. Forces are measured with things like scales, like a bathroom scale, or a spring scale, like the one that's in the produce section of the grocery store. And force has the units of newtons. We abbreviate this capital N, and this is named after the famous physicist Isaac Newton, and we're going to talk more about him in the next chapter. We represent forces with arrows, and this is because a force is a vector quantity. Remember, a vector is something that has size and direction. So examples of vectors are displacement, velocity, and acceleration. So the direction of the arrow is the direction of the force, and the length of the arrow is how strong the force is. So if I have an object here, if I have a ball, and I push on this ball, and I push it to the right with a really, really large force, that is what my force arrow is going to look like. If instead I push on that ball with a really weak force to the left, that's what my force arrow is going to look like. So we can represent different forces acting on an object or multiple objects simply by drawing arrows. When we have more than one force acting on an object, we have to combine them together to find the net force, or the overall force acting on an object. So in this picture, we have blue shirt guy and red shirt guy, and they're playing tug of war. Red shirt guy is pulling on blue shirt guy in this direction, and blue shirt guy is pulling on red shirt guy in this direction. Let's say that red shirt guy is pulling with a force of 5 newtons. And blue shirt guy is also pulling with a force of 5 newtons. Both of these forces have the same magnitude. They have the same size, but they're in opposite directions. So, because force is a vector and they are in opposite directions, one of these forces must be a negative force. I'm going to go ahead and call blue shirt guy's force negative, just because in my mind moving left seems negative. So that's just the convention that I've chosen for this problem. Now if we find the net force, what we have to do is we have to add these together. So we have red shirt guy's force of 5 newtons, and we add blue shirt guy's force of negative 5 newtons, and we end up with a net force of 0 newtons. What that means is these forces are balanced. They are equal in magnitude and opposite in direction. And what will happen when we have balanced forces is there will be absolutely no change in an object's motion. So this is a stalemate right now. Blue shirt guy and red shirt guy are going to pull and not move, stay exactly where they are until somebody gets tired. So let's say the red shirt guy gets tired and he starts pulling with a force instead of 3 newtons. So what that will change is our net force now is 3 newtons plus minus 5 newtons. And so our overall net force acting in this scenario is minus 2 newtons. What that means is that overall we are going to have 2 newtons of force moving in this direction. I know that's not to scale, but we have 2 newtons of force moving in this direction. So the overall motion of what is going to happen in this scenario is blue shirt guy will start to move this way, and red shirt guy will get pulled that way because he is no longer able to match the force of blue shirt guy. Now, when forces are unbalanced, an object will accelerate. An example of this is a man parachuting before he deploys his parachute. So the forces acting on him here are the force of gravity down and a little tiny bit of air resistance acting upward. Now, as he falls, he's going to speed up and speed up and speed up and speed up because the force of gravity is much, much larger than the force of air resistance acting on him. This isn't always the case, but it will happen for the first part of a skydiver's journey every single time. Now, there are many common forces we deal with on a daily basis. We deal with a lot of pushes and pulls. Otherwise, we wouldn't move, we wouldn't go anywhere, we wouldn't be able to interact with objects, and it would be horrible. But there are two really common forces that we interact with every day, and those forces are friction and gravity. Friction is a force that opposes motion when two things are in contact. And there are four main types. There's static friction, which keeps things from moving. There's sliding friction, which is the friction between two objects that are in motion relative to one another. There is rolling friction, which is the friction between a surface and a rolling object. And then there's fluid friction. And fluid friction is the friction between a moving object and the fluid it is moving through. So, an example of fluid friction is air resistance, because air is considered a fluid, as are all liquids and all other gases. And as something moves through air, the air molecules actually interact with that moving object and cause resistance, thus a fluid friction. Gravity is an attraction between two or more things that have mass. So we tend to think of gravity as the attraction of objects to the surface of the Earth. But it turns out the Earth is also gravitationally attracted to all objects on Earth because it is a mutual attraction. So I am gravitationally attracted toward the surface of the Earth, but the Earth is also gravitationally attracted to me. I'm also gravitationally attracted to all of the chairs in my classroom, or the whiteboard, or my water bottle, or my computer. I am gravitationally attracted to everything that has mass, and everything that has mass is gravitationally attracted to me. When we talk about gravity, most of the time we are going to be talking about the Earth's gravitational pull on an object. So we can abbreviate that. Instead of saying the gravity from the Earth acting on this thing is, we can just say gravity, because in our frame of reference, 99% of the time, the gravity we are talking about is the gravitational pull between an object and the Earth. Now, friction and gravity actually interact a lot, and they interact during free fall. So an example of free fall is when somebody is going skydiving. So if this parachute has not been deployed yet, and this little skydiver is in free fall, he has the force of gravity pulling down on him and some air resistance acting up. And the force of air resistance is less than the force of gravity, so he's going to speed up as he falls. But it turns out as he speeds up, the force of air resistance increases and increases and increases. So as his speed increases, the air resistance also increases until the point when the air resistance acting on him and the force of gravity are equal. At this point, this is what we call terminal velocity. And this is the downward speed at which the force of gravity equals the force of air resistance, because now we have balanced forces equal in magnitude and opposite in direction, so our net force is 0. Thus, the motion of the object will not change. He will continue to fall with the same speed in the same direction until the parachute is deployed. So terminal velocity for a human being is about 120 miles per hour, but there are some skilled skydivers who can go into a controlled nosedive and get up to speeds of about 200 miles per hour before the force of air resistance balances the force of gravity. So now that you know a little bit more about forces, go ahead and answer these homework questions and have them ready to turn in tomorrow.